Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy, and today I'm excited because I get to finish up a project I started some months ago. We've been looking at how we determine the distance from the Earth to the Sun, one astronomical unit, and today I'm going to finish up with pretty much the ultimate way of doing it, for amateurs at least, and that is the transit of Venus. Now, very few people knew about Henry Cavendish's experiment where he demonstrated mass attracting mass and measured the density of the Earth. However, 30 years before, the transit of Venus was on everybody's mind, so much so that they called the 1760s the transit decade. Everybody was interested in this. And finally, by using the transit of Venus, we may be able to put a number on the size of the solar system. Now, how does the transit of Venus work? Well, first of all, here's a picture of the Sun. Now, as you can see, there's a solar filter here, and we've got a couple of translucent sunspots here on the surface of the Sun. When objects pass between us and the Sun, we see them in silhouette, much like this airliner. We can even see the contrails behind the airliner in silhouette. Right here is the planet Venus. Now, when people look at Venus from different locations on Earth, they will see it pass across the Sun, but in a different location than anybody else. By comparing the locations that two observers of a known distance apart could see Venus cross the Sun, we can determine the distance from the Earth to the Sun using something called parallax. So let's cue up the music and see how the transit of Venus was done. Okay, so let's go ahead and have a quick look at the basics of what the transit of Venus involves. So here's our little diagram. Now, here's Earth, here's the Sun, there's Venus. Well, first, if you're at a point where Venus is at your zenith, in other words, directly over your head, you're going to look past Venus and see the silhouette of Venus, say right there. Now, if you look at another point on the Earth, and you look past Venus at a non-right angle, you're going to see Venus, say, up here. First of all, how do we measure the distance between those 2 points? Well, that's rather simple. Now, we know that the diameter of the Sun is 31 arc minutes, say. That changes on a day-to-day basis, but we're going to know what it is precisely to the arc second on the day of the transit. So if we know that this diameter is 31 arc minutes, we can figure out how many arc minutes and arc seconds separate that image of Venus from that image of Venus using this 31 minutes as a scale. Now, the interesting thing about that is that gives us that angle right there. And that angle is the exact same as that angle. So now we've got a triangle and we know one angle. We don't know the length of any of these sides, but we know that angle. So can we get a side? Well, yes, we can. This is a certain latitude. If we take the radius of the Earth times the sine of the latitude, we get this distance right here. So now we have a leg of the triangle, and we have the opposite angle of that triangle. So we know that that's a right angle, and we can actually measure that angle there as well. So now we've got 3 angles and we have one side. We can solve for this triangle. So what does that tell us? Well, it tells us this distance right here, from the base of the triangle to Venus. Well, how does that help us? Well, we know that this is the radius of the Earth. And we know that this portion of the radius is the radius times the cosine of the latitude. And once we solve for that little segment right there, we can determine the length of that whole leg. Now next we have to go to something called Kepler's laws of planetary motion. Now, the third law of planetary motion is that radius cubed is proportion to time squared. Now, what does Kepler's law allow us to know? Well, we know that this distance from the center of the Earth to the center of the Sun is 1 astronomical unit. That's just by definition what 1 astronomical unit is. And we know that of that, Venus is 0.72 astronomical units. That means the distance from the center of Earth to the center of Venus is 0.28 astronomical units. But by solving for that triangle, which we've already done, we actually have numbers that we can plug into this formula. And as a result, we can get the distance from Earth to Venus. And by dividing that distance by 0.28, we get 1 astronomical unit. It's just as simple as that. Now, one thing that I want to point out is the only way that that works, that's kind of a modern way of doing it. We have to be able to tell that these two pictures that we measured our distance from were taken at precisely the same time. We have the capability of getting that sort of coordination now. Now, when Captain Cook was doing it in 1769, there was absolutely no way that he could assure that his observations were timed precisely with the observations at any other point. They didn't have that type of communication. So how did they do it? Well, they went back to the original paper done by Edmund Halley of comet fame, and he wrote this paper in the early 18th century, knowing that he would never live long enough to see a transit of Venus. So let's go ahead and see his method for doing it and how you could do it without being able to coordinate times. Now, they tried to do this in 1761, but that was in the middle of the 7 Years' War, and I mean, there was all sorts of drama involved with that. There was piracy and all sorts of other things. They weren't able to get a good measurement in 1761. They got some, but they weren't satisfied with it. They realized they only had one more shot, and that was in 1769. If they missed that one, they wouldn't get another chance for another 112 years. So what they did was they sent out 175 or so expeditions all over the world. And what they wanted to do was they wanted to mark the passage of Venus. Now, there are 4 times that are critical in the passage of Venus. Let me show you what they are. The first one is when Venus first touches the outer edge of the sun. The second one is as soon as Venus is fully within the sun. So in other words, as it's coming across, you can't really see this first one really well because you're seeing a black planet on a black background. However, you can see this bulge coming into the body of the sun. And because Venus has an atmosphere, this is a little bit more difficult than you would think it would be. But what they were looking for was the very instant, the second, that you could see light between Venus and the edge of the sun. That was defined as the passage. And then about 6 hours later, you would get over to the other side of the sun. And you would get a point where Venus was just touching the surface of the sun. Now, the way that you would tell that is you'd watch Venus go across, you'd see the little black drop of the atmosphere, but you would suddenly lose the ability to see light between the edge of Venus and the edge of the sun. That was marked as the third phase. And the fourth phase is when Venus cleared the sun. Now, because Venus transited the sun at a set rate that was visible all over the world, we could actually time the distance between number 2 here and number 3 here. And by timing the distance, we knew the length of this line. Hopefully that makes some sense, because if we have a certain velocity that it's going across the planet, we know that it took 8 hours, 4 minutes, and 32.5 seconds. We could tell you exactly how long that line was. Now, if you go to another observation point they're measuring the same thing, and they may have 7 hours and 56 minutes. So that means that the line is a little bit shorter. So it'll only fit, say, down here or up here. And depending on where you are on the Earth, you could tell which one it was. Now, the other thing that you can do is they recorded where the sunspots were, and they could match up the sunspots as well. But basically what you did was you got another observation here. This distance right here in arc minutes and arc seconds, that was the parallax distance. And again, all you had to do use that distance, calculate that angle, get this one right here. Now you've got your right triangle and you've got your distances. Okay, so let's have a look here. So here are our two observers, and they're looking past Venus. Here's what the southern observer sees. Here's what the northern observer sees, and the path of Venus goes across the sun like so. Notice that this line is a little bit longer than that line. By calculating the distance between these two, by comparing it to the angular size of the sun, we know this angle. With that, we know that angle. We determine the length between the center of the Earth and Venus. That's 0.28 astronomical units. So we divide it by 0.28, and that gives us the distance from the center of the Earth to the center of the sun. Now, in the modern times, we can actually coordinate these by time. So here's a shot taken in Afghanistan and another one in California. And if you superimpose those two, looking at Venus here and a sunspot here, you can identify Venus here and that same sunspot. These are clouds, by the way. You can combine those two photographs and you end up with something like this. So here's the sunspot. Notice there's one Venus, there's a second Venus. So that distance right there is the parallax. Well, now we know how the transit of Venus was calculated. Join me next week as we go over an actual observation from June of 2012, the last transit of Venus. And we'll go ahead and calculate one astronomical unit, the distance from the Earth to the Sun, based on two photographs. So until then, this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by. Make sure you hit that like and subscribe, and consider a Patreon or a membership in our channel. In the meantime, we'll see you later, and you take care.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for me. Feel my brain getting real sore. Above the science guy. Above the science guy.